For this section 5.3 called Circuit Training, I'm using the basis of the book, but using something that I find to be a little bit easier in working with this kind of thing. It all goes back to the story that is in the book about Euler being asked that the citizens of Königsberg would want to take a walk a nice summer's evening, and there was 4 regions that are connected by 7 bridges. And a way of paraphrasing it is they tried to find different ways to walk across each bridge once and only once and end up back home again, but they couldn't do it. So they went to Euler and said, hey, is there any way to do this? Well, Euler looked into it and he made some discoveries. If we look at the 7 bridges of Königsberg, we look at it on an old map. The river, of course, is colored more blue, and the bridges are the fine-looking shapes that are green. And it's the basic location of the bridges. So, from the different regions, can you go across each bridge once and only once and end up back home after you cross all 7 of them? Well, this is a fine map to do this on, but maybe for our purposes, it's a little bit easier to use a map that looks a little bit more like this. This shows just the river and the regions. We see that the island in the middle, they're calling A. At the bottom, that section of land is B. On the top, it's C. And D is, of course, after the island as the river's soon flowing in that, from left to right. D is this section of land over there. If we drew this in a more mathematical way, it could look something like this, where, again, we have region C, A, and B, and D on the other side, and each vertice, or each dot, is represented by a dot, and it is given a letter, and the bridges would be represented by the lines or the edges. Now, Euler did this study, and he came up, as he did this study, he developed a few simple concepts. The one is an Euler path, sometimes referred to as an Eulerian path in English. But with this kind of path, you visit each edge exactly once. So if you were to trace this with a pencil, you would start at a point, and you'd be able to go across each edge, each bridge, once and only once, and get across each bridge. You may go through the same vertice more than once, but that doesn't matter as long as you only go across each edge once and only once. An example of this would be in the shape you see here. Now, the other thing I didn't mention about an Euler path is that the starting and end points are not necessarily the same. So you can go through each edge, but you may not end up back home, so to speak, to use the Königsberg example, or you may simply end at a different place than you started. Now with this one, we notice that if we start at the top or bottom of it, we can't draw it. We can't draw an Euler path. We get stuck. But if we start on the left one or the right one, we can. We can trace it across up to the top one, down to the one on the right, go across the middle to the first point where we started, and go down to the bottom point, and then back up to the one on the right. And we know that we went across each edge or each bridge once, and only once. We didn't end up where we started, but that's fine. An Euler path visits each edge once and only once, and the starting and end points are not necessarily the same. An Euler circuit is like a path, except that the end points and the starting points, it's the same. So, you visit each edge once and only once, and you end up where you started. So, looking at the same shape but taking away the center line, this would be an Euler path. You can start on any of the 4, go around the edges, and you end up right back where you started. So, these are rather simple shapes. They can get a little bit more complex. Now, when we're looking at this, we'd say, well, how many odd vertices are there? Well, what's an odd vertice? Well, we're also going to have an even vertice. An odd vertice is you look at each dot, each vertice, and you count how many lines come into it. Now, it doesn't matter where the other end of the line goes, it's just how many goes into each point. So on the first one, if we look at it, the one on the left, we see that there are 3 lines that go into it. So 3 is an odd number, so that makes that an odd vertice. If we go to the top one, I'm looking at the Euler path. If we go to the top one, we see, well, there's 2 lines that go into it. It doesn't matter that it's shared with the other point, it's just how many lines go into this point. And there's 2. Well, 2 is an even number, so that's an even path, or an even vertice, excuse me. And we look at the one on the right of the Euler path, and we say, well, there's 3 lines that go into it. And 3 is odd, so it's an odd path. And if we look at the bottom one, there's 2 go into it, 2 is even, so it's an even vertice. On the Euler circuit, when we look at it, we realize also that all of them have 2 lines that go into them. So all 4 of them are even. So again, an odd vertice, the number of lines that go into it is odd, so it's odd. An even vertice has an even number of lines that go into it, so it is even. Now here's 6 graphs. If you want, you can pause the video and try and figure out, are they a path, a circuit, or neither? So when you're done, just restart the video. Now looking at these particular videos, or excuse me, shapes, let's look at each one. If we start with graph 1, if we start here with graph 1, we notice it's this kind of star shape. Let's keep track of the number of odd vertices, the number of even vertices, and whether it's an Euler path, circuit, or neither of these. Well, if you had a chance to figure this out, you can say, well, yeah, you can go through all of these, since you can go through all of them once and only once, and there you end up where you started. It's a path. So, or excuse me, a circuit, not a path. Now, in figuring out the order, one way to communicate this, there's many different ways. The book uses a different method, but this method's a little bit easier, I think. I'm starting with edge 1 there, and then I go to edge 2, and then 3, 4, 5, 6, 7, 8, 9, and you go in, 10 goes into the middle, 11, 12, 13, 14, 15. Hopefully just looking at, by numbering each edge in the order that you would trace it, you would know that I started at the left tip of the star and went around the outside, and then before closing off the star, then went around the inside and then finished it. So there are many different ways to do this, but this is one way that clearly communicates a solution for the circuit, and it is indeed a circuit. Now, when we go through, we look at all of these, we realize, well, all of the points on the outside of the star have 2 lines that go into it. So there's 1, 2, 3, 4, 5 of those. So there's 5 even vertices, since there's all 5 of them have 2 lines that go into it. And then the 5 vertices, or dots, in the middle of the star, we realize there's 1, 2, 3, 4. And that's true for each of them. There's 4 lines that go into it. And don't let the fact that it looks like the lines are straight trick you into thinking that there's 2. There's actually 4 lines that go into each point, looking at it as line segments. So 4 is an even number, so all 5 of those are also even. So there's a total of 10 even vertices and no odd vertices. Now if we look at this shape, we can do, hopefully you had a chance to figure it out, but this is also a circuit because we can follow 1, 2, 3, 4 on up to 9, and we realize that yes, we can go through each edge once and only once and end up where we started. If we count the vertices, we say, well, the points of the triangle, the top, left, and right points, they each have 2 lines that go into it, so all 3 of those are even vertices. The ones at the midpoints of the outside, well, they each have 1, 2, 3, 4 lines that go through it. So they are also even. So all 6 of them are even. There's no odd vertices. So it's an Euler circuit. This one's a little bit different. And if you had a chance to figure the solution out, you realize one possible solution is this. There can be more than one solution, so that's why we label it. That shows people this is how I solved it and how I'm referring to it. But there can be other solutions. So we can go around the diamond shape on the left side, then go across the middle and go around the diamond shape on the right side. And if we count up, we look at the two diamond shapes. We realize the one that has the one line connecting the one diamond to the other one, on both of those you count there are 3 lines going into each point on the respective side of the triangle that it's connected to. And the other 3 points of the triangle each have 2 lines in, so there'd be a total of 6 that are even and 2 that are odd. And we notice that it's a path, not a circuit. This particular shape, we figure we can do this. It's also a path, but we have to, the only way to solve this is to start either at the top or the bottom where there's 3 points going into it, where the diagonal cuts it off, so to speak. So there's not as many solutions to a path as there are a circuit, but there's still, in this case, 2 possible solutions. And maybe you could go different directions to get another 2. Now, again, we count the one that has the diagonal to it. The top has 3 edges. It's odd. The bottom of the diagonal has 3 edges. And the other 4 points have 2 lines going into it, so it's even. So we end up with 2 points and 4 points. So it's a path. The 5th graph, if we look at it, we couldn't figure out a good way to do this, could we? And if we start counting, we realize that all around the outside of it, if we start at the top left, there's 3 edges that go into it, so it's odd. The top on the right has 3 edges, the bottom right has 3 edges, the bottom left has 3 edges, so there's 4 ones that have odd, and the one in the middle has 4 lines going into it, and that's even. So it has 4 odd and 1 even, and it's neither a path nor a circuit. Couldn't figure out how to go across each edge once and only once. To get all of them transferred, you have to lift your pencil or you have to go over an edge twice. So it's not a path nor a circuit. The last shape is kind of similar. It's not a path, or it's also not a circuit. If we look at the top left has 3 edges going into it. It's odd. The top right has 3. The bottom right has 3. The bottom left has 3. So they're all odd. And we look at the smaller square inside of the bigger square, and well, each of those corners also has 3. So when we look at it, we say that there are 8 edges that are odd, 8 vertices that are odd, and no even, and it's neither an Euler path nor an Euler circuit. Now, if we look at just the table that we created, can we notice a pattern here? Well, yes, we do. If you have a graph and it has 0 odd vertices, it's going to be an Euler circuit. It's possible to draw through each edge once and only once and end up where you started. If a graph has 2 odd vertices, then it's going to be an Euler path. You can go through each edge once and only once, but you won't necessarily start where you ended, end where you started. And we realize, well, we would need more examples than this to figure out the rest. But the reality of it is, if there are more than 4 odd vertices, it's not going to be a path, nor will it be a circuit. So in figuring out if it's a circuit or a path, it's pretty simple. Count all of the lines going to each vertice. If there are no odd vertices, it's a circuit. If there are 2 and exactly 2 odd vertices, then it's an Euler path. And say, well, what if there's 1? Well, the reality of it is, if you draw this correctly, you can never have a graph that has just 1 odd vertex in it. If you get something like that, you probably made a mistake somewhere or missed a vertex, because there will be 0 odd vertices, 2 odd vertices, or more than 2 odd vertices. So, if we look at the 7 bridges of Königsberg, is there a solution to this? Well, we look at the top and say, well, there's 3 edges going into it at point C. At point A, there's 5 edges. And at B, there's 3 edges. And at D, there's 3 edges. All of these are odd. So we say there's 4 odd vertices. There's no even vertices. Once you have more than 2 odd vertices, it's neither a path nor a circuit. So Euler could confidently tell these people that there is no way to cross each bridge once and only once, end up back in your doorstep. Now, the special homework assignment is for you to make 3 Euler paths and 3 Euler circuits yourself. It's not actually too hard. It just takes a little bit of thinking and you can come up with stuff. This assignment gives you a chance to use your creativity and any artistic talent that you have. But even if you aren't artistic, it's not hard to do. Now, 2 of the paths and 2 of the circuits must have at least 8 vertices. And 1 of each, 1 path and 1 circuit, must have 12 or more vertices. That may seem like a lot, but once you get into it, it's not too hard. With each path and each circuit, label the number of odd vertices, the number of even vertices, and whether it's a circuit, path, or neither of these. As you're doing this, make sure all dots are visible. Make sure all vertices are visible, and circle any odd vertices in a color that stands out. Don't use the same color as the pen or pencil you're using to draw it. And then show a solution as we've been doing by labeling each edge using numbers. Nice if it could be at a different color than the line is, but do it in the order of the solution. So I know that you know how to do it. It's hopefully not too hard to do. An example of this would be like this. This example, it doesn't have enough points in it. It's just a simple one. Yours have to have 8 or 12. But this one, obviously, we start over on the left. Excuse me. We start over on the left side. We go through the first edge, and the second little loop there to the third one, fourth little loop to the fifth one to the end. This is obviously a path, but all of the odd vertices are circled. That's what the red is. And simply the list then shows there's 2 odd vertices, there's 2 even vertices, and it's an Euler path. So it's not too hard to do. Some examples from students who have done this in the past. You can use different kind of geometric shapes. It doesn't have to be something hard. Like I said, if you want to do something that is artistic, you can. All of these are clear. Occasionally, someone forgets to put in a different color or circle a point. Don't worry too much about it as long as it's pretty clear. All of them say the number of odd vertices, number of even vertices, and it's an Euler circuit or path. Well, technically, I guess there won't ever be any neither because I'm not asking you to do any of the neithers. But you notice with the umbrella, instead of circling it, they just used a different color dot for the odd ones and the same color for evens. And the house is the same way. So it's really easy to tell, even though they didn't circle it, which ones the odd and even vertices were. Here are some more examples, kind of an envelope here. It gets a little bit more complex. So you can see it's rather easy to get something that's complex. The top one only has 11 points in it, 11 vertices. It's not a lot. And it looks nice. The next one has 19 vertices in, so it's wonderful. It's more than 12. But it's a nice little kind of shape of a flower. And we can see easily with both of these, we can see which ones are odd as they've highlighted it. You know the solution just because you can follow the numbers 1, 2, 3, 4 and on up. And it's not hard to do. Someone else who really enjoyed this kind of assignment went through and even used some colors and just made some shapes and did an excellent job. Your work doesn't have to look this good. It's just an example of someone who put a little extra effort into it and enjoyed what they did. So hopefully you can enjoy this too. As you can see with the car and the house, they put in some other things to make the shape more obvious that obviously they didn't count as part of the drawing, and that was quite okay. It was clear which ones they were calling were the vertices and which edges they were using as well. Now, on the last example, we have someone who took a lot of time. I'm not expecting anything like this, but this person enjoyed this, enjoys making shapes and was very artistic. And so this was just a fun thing to do. One of the few assignments you may get in college where you can just go back if you enjoy artwork, have fun with it, spend a little bit more time, but it's because you're doing something you enjoy, and tie a little bit of math into it. So hopefully you can enjoy this and have some fun with it as well. If you have any questions, send me an email. Oops, I forgot about this one. This person had made this little turtle. I was using an older system to identify this. Once she made it, it was on her paper with other ones, and she said, "Whoops, I made this and I forgot to count, and this is not a path nor a circuit." So she just simply said, "Don't count this one," and that was fine. So if you make a mistake, you don't have to erase it, cross it out. Just say, "Please don't count this one." And she had 7 charts, graphs with this, and I still got to see her artistic talent with the turtle. It's kind of nice.